Well, I think her introduction lets you know that my path to a Nobel Prize has been somewhat unconventional. And I just wanted to start off with giving you a quick synopsis of my last 30 years of my life. So I started work both before and after whatever the most critical discovery is that is recognized by the award. And that was not the case for me. So, like I said, when Darwin Molecular closed in 2004, it was a real hard stop for me. It was from University of Washington, and the point that I want to make here, in my case, and I think it's probably true of most scientists who have successful careers, is the importance of good mentors. And so I was really fortunate to, when I started as an undergraduate at UW, I really was set on wanting to apply to medical school at the end, so I was going through the whole
Thank you so much for the presentation. It was really wonderful. My question was specific to your research. You said that you had discovered there is a connection between FOXP3 and IPEX, and I was just wondering how you're able to discover that connection, and also what implications that connection had onto human health, not just mice.
So one of the first things we did, of course, when we sequenced the mouse FOXP3 gene, we confirmed that there was a human homolog, not surprisingly, and the IPEX condition had already been mapped to the same general region of the X chromosome, and there was a lot of, if you just read the literature and descriptions of the IPEX condition in humans, there was a lot of overlap with what was being seen with scurfy, and so I honestly don't remember who made the first move, whether it was Darwin who reached out to the UW clinical geneticists or vice versa, but we ended up collaborating together on, and also the OHSU folks, and it was a nice collaboration, although it was pretty straightforward. It was, we have the gene and you've got the DNAs, and so. But I think that work has really progressed since. I mean, that having some understanding of the molecular basis of the human condition has helped. I don't know how, it has helped in understanding, better ways of approaching managing that condition.
Thank you, Mary. We have the
question is also about the research. Could you go back to the figure with the comparison of 3 lymph nodes with 3 different phenotype of mice? And I want to ask that one. Could you tell us more about the transgene? You mentioned that the scurfy protein is from FOXP3, which is 2 base pair insertion mutation. So did you insert 1 extra base pair, or you simply transfect a healthy or well-type allele into the mouse like zygote or embryo?
Yeah, the transgene was the wild-type version of FOXP3, so it did not have that 2 base pair insertion. We wanted to try to rescue the scurfy defect in mice. So I wanted to put in a transgene that was going to be expressed as similarly to the endogenous gene as possible. So we just took a big chunk of genomic DNA with the thinking that the transcriptional control elements were going to work okay, the exon intron splicing was going to work okay, and it did work, in fact. And we generated about 6 different lines of transgenics with a wide array of copy number, and in fact, overexpression of the wild type gene does give you kind of an opposite phenotype to what you see in scurfy. So smaller lymph nodes and.
Do you mind to share? I have a follow-up question. Do you mind to share which viral vector you used to transfect this gene, if you remember?
Well, it's not an infection or transfection. It's a microinjection into mouse embryos, and we took just a restriction fragment out from a back clone, which is bacterial plasmid, and I just transferred that into a cosmid vector, I think, to propagate it. So it was, we did a lot of, we had the sequence, so then we just found a restriction enzyme that would excise only the FOXP3 gene and subclone that into a cosmid vector, and then use that to purify DNA and do the microinjections into mouse.
Thank you very much.